Welcome to 1.2 significant figures. Uh, let's get started. We'll discuss first of all, significant figures are a very important part in chemistry because it gives us the accuracy that we are allowed to measure to, right? So if one number is less accurate than the other number, we can't assume that the accuracy is the other number. We have to make it so that the uncertainty, the accuracy is known, so that people, whenever people replicate the same experiment, people know the precautions. So significant figures are really important. And what are they? They are the numbers that are considered important, right, when doing a calculation. Uh, this one's specifically just for a calculation, but really what significant figures are what I just said, right? So for example, this number has 5 significant figures because it has 5 digits, and I'll give you the rules for significant figures. The significant figures, uh, all numbers 1 to 9 are significant, right? So if I had 2.583, they're all significant. They're all significant. 2.583, 4 significant figures, 4 significant figures, because there's 4 numbers, right? So in this case, um, the 0 might not be significant, or it might be significant, right? There's a chance that it's significant, there's a chance that it's not significant. We've got to analyze the number first. So for example, in this number, 3.408000, all the numbers are significant, because the 0 before the 8 is significant because it shows the accuracy, and there's an 8 after, so if there's no 0, it will be read as 3.48, which is not equal to 3.408, and then there's 3 zeros at the end. Now I don't know, but some people might count it as not significant. It is significant because there's no point of putting those 3 zeros if it's not significant. I could have just said 3.408, then it will be to 4 significant figures, but I put 000 in there to tell that it's significant. It's accurate up to 7 decimal places, up to 6, which is 7 significant figures. So that's why. However, if we're looking at 4200, the 2 zeros are not significant, right? They're not significant because if I write 42, we don't know that it's 4200. If you read this, you will know that it's 42, not 4200. So if you want to make it significant, you gotta put 4200 dot. Then it becomes significant. It will be 4 significant figures, right? But in this case, it's only 2 because it's the 4 and the 2, right? The 4 right here and the 2 right here, right? So how many significant figures are in this number? The 0 is significant, so we have 1, 2, 3, 4, 5 digits. 5. I'm just gonna shorten it to sig figs, right? Next we have 0.6803. Now the 0 in the beginning is not significant because I could have just said 0.6803, and that would be significant as well. The 0 in the beginning is not significant. It's like putting 0.0320. It looks like there's 5 significant figures or 4, but there's only 2. It's only 320. But the 0 is a placeholder, so it's not significant, and then the 2 zeros at the end are obviously not significant. So the 0 is not significant. This is 4 sig figs, right? 0.300. The 0 in the beginning is not significant, but the 2 zeros at the end are significant because there's no reason why you would place the 2 zeros at the end if they're not significant. So 3 sig figs, right? And then 2.139006, they're all significant because the 0 zeros before the 6. If you write 2.1396, it's not equal to 2.139006. So 7 sig figs. Okay, let's move on to the next one. So how many significant figures can you deduce from the scale? What is the accuracy? I'll phrase it as, what is the accuracy that you can deduce from this scale of measurement, right? So if you're looking at this shape right here, if you look really, really closely, the increments, right? The increments are 0.1, right? So you can have 1.1, 1.2, 1.3. That's already two sig figs, two significant figures. 5.0 centimeters. We know that it's equal to 5.0 centimeters, at least two significant figures. It's a known measurement. But when you're estimating, you want to give an extra significant figure because we're estimating, right? And then you can put you can put like a plus or minus 0.05 centimeters. You can put this at the end in order to tell the uncertainty. But when you're looking and when you're estimating, you want to, okay, because if I zoom this in, see, that does not look like it's on 5 exactly. It looks like it's a little bit on 5, maybe 5.01, but I just put 5.02 because that's what I can see from this. But 5.02 centimeters is the estimated value. So you can estimate, you can deduce 3 significant figures the most. Is it really significant to go to the 4th value? Well, we can't see the 4th increment. We can't see the 4th value increment. So no, not really. Same for this one, right? It goes by 0.1 every kilogram. It goes by 0.1, and the big scale has 1. So 0, 1, and this is 1.1, roughly 1.12. And you can also do 1.1 kilograms is the known measurement. It's two significant figures, but our estimated value is the amount of significant figures that we can deduce, which is 1.12 kilograms. Okay, so estimate the measurement to the appropriate amount of significant figures. We have 2 and 3 right here, so that's 2.5. That's 3.5. That's 4.5, and each of them is 0.1 because you can count 10, right? So 4.0, 4.1, 4.2, 4.3. But since this is in the middle of 4.3 and 4.4 and it's about this much, we can deduce that it's about 4.32 or 4.33. So 4.32 or 4.33 pounds per square inch, right? And we've done units, so I've got to make sure we have to write it like this, because if we write it as PSI, you're not going to know what it is. You're just going to know it as 1 unit PSI, and you don't actually know it's pounds per square inch. So now if you look at this, it denotes every 0.5, but every interval is still 0.1. So it's not any more significant, right? This is 3 sig figs. This is also 3 sig figs because our deduced value is 1.25. 1.25 centimeters, right? 1.25 centimeters. It's in the middle of 1.0, 1.5, pretty much exactly. So there you go. Next, we have more sig fig rules. When you're adding or subtracting two figures, you round the result to the significant figures that both numbers have in common. And it might look a little bit confusing, but here's my example. So basically, the amount of significant figures that both numbers have to the right is the amount of significant figures you round to. So for example, we're gonna do this right now, right? So 3.3289 plus 843, right? We're gonna add them together. What's the significant figures that both numbers have in common to the right? Correct? This number. So it's the only number that both significant figures have in common. So 846. And we don't really need to add the 0.3289 because it rounds down to 846. That's our answer. Alright, 4.03 plus 3.4 is equal to 7.43, but we only take the 7.4. because closest to the amount of the significant figure that both numbers have in common is the tenths unit, and it's the most to the right. Let's add these two this time. Plus 4.165 is equal to 13.068, right? But in this case, the 3 and the 5 is in the same significant figure position as the 8, so we can include that, right? Okay, let's subtract these two numbers. We're just not going to do these because we're going to do this. We're not going to do the second one because we don't have enough time, frankly. 183.98 subtract, we will get ourselves a nasty number, really nasty number. 0. 2 subtract 9 is, no, 12 subtract 9 is 3. 7 subtract 3 is 4. 13 subtract 18 is -5. 13 subtract 8 is 5. And then 0 subtract 1 is -100. So then we gotta do this. This is not the way that I do it, by the way. I'm just trying to be a little okay, but we do know that this is our significant figure that we have to get rid of. So we can just do 45, -45.697, right? We have to round it up to this 9, so we have -45.7. But it's not -45.7. We have to add a 0 in there because the 0 signifies that it's that accurate. So same thing with this 8.01 subtract 20. Let's actually do it the simple way. We'll do 20 subtract 8.01, which is 11.99, but then we'll make it negative, right? And it's accurate to this position, so we round it up to -12. That is how significant it is. Right, in this case, 3.46 plus 4.34, when you add it together, you'll get 7.80, but we keep the 0 there. We don't round anything because it's the same decimal place. See, the 6 and the 4, same decimal place. We don't round, right? Okay, let's go to multiplication and division. When you are multiplying and dividing, you round the number to the number of significant figures that the number that the lower significant figure. This is not right. This is not right. Round the number of significant figures that the number with the lowest amount of significant figures have. So, for example, 3.9 times 6 is 23.4, but 6 has the lowest amount of significant figures, so we round it to one significant figure, which is just 20. 20. That's it. 103 times 56 is a big number. It's 168, so 5768. But 56 has two significant figures, so we round it up to two significant figures, 5800. Right, I'm gonna write these in scientific notation. So 2.0 times 10. Actually, no, 2, because scientific notation defines how many significant figures you're supposed to have. So 2 times 10 squared. No, times 10 to the first power. Right, in this we have 5.8 times 10 to the third power. Okay, I chose easy numbers to divide because I did not want to use a calculator. So 0.36 divided by 0.4 is 9 over 10, 0.9. But which one has the lowest amount of significant figures is 0.4, so it's just 0.9. That's our answer. We don't have to round it at all. But it's 9 times 10 to the negative first power. Right. 3.57 divided by 20 is 0.18, so 0.1785, I think. 0.1785, correct me if I'm wrong, but it still rounds up to 0.18, and that is 1.8 times 10 to the negative first power. Because there's 20 and two decimal places, two digits means, actually no, it's 20, so it's one significant figure, right? I nearly made that mistake. It's one significant figure. Rounded to 0.2. 0.2 means 2 times 10 to the negative 1. So I thought I'd just add the temperature formulas in because it's you have to know this for the temperature calculations that we're going to be doing later in the course. So here are temperature formulas. Kelvin is equal to Celsius plus, there's three types of temperatures: Celsius, Fahrenheit, and Kelvin. Right? The ones that you normally see in North America is Fahrenheit. One that you normally see everywhere else is Celsius, and Kelvin is used in scientific equations. Temperature measures the amount of kinetic energy that a substance has, right? Um, motion will get you will result in a higher temperature. So the amount of kinetic energy will determine the temperature. If you make steam, then the steam rises up, becomes a gas that has high kinetic energy because it moves a lot. It rises up, right? So we'll just start. So if we are at 0 Celsius, we plug it into the formula. 0, I already know all this. If you want to do it, you can do it. Pause for 5 seconds. No, you can pause right now, but I'm going to do it right now. So if you plug 0 in for Fahrenheit, you'll get 9.9 over 5 times 0 plus 32, which is just 32. And then 0 plus 273 is 273. Fahrenheit 86, you plug this in, 86 times 32 is 54. 54 times 5 ninths is 30. And that is 303. Negative 134, you plug that into Fahrenheit. Negative 134 times 9 over 5, that is a naughty number. Negative 134, we're going to round it to the nearest degree. Over 5 is 241, negative 241.2, added to 32 is negative 219. Negative 219. And Kelvin is negative 134 plus 273, which is 139. 139 degrees Kelvin. 263 degrees Kelvin is 10 degrees Celsius, which is 50 degrees Fahrenheit. And I remember this, 212 degrees Fahrenheit is 100 degrees Celsius, which is 373 degrees Kelvin. And that's it for today's episode. If you like to press the like button. If you want any more questions about significant figures, I went through it kind of fast. You can post them down in the comments below. And next chapter, we will be starting on the actual chemistry stuff of the chemistry course. So I'm looking forward to that. And until next time, see you later.